Entropy is surely one of the most perplexing concepts in physics. It's variously described as a measure of a system's disorder, or as the amount of useful work that you can get from a system, or as the information hidden by a system. Despite the seeming ambiguity in its definition, many physicists hold entropy to be behind one of the most fundamental laws in all of physics. The great astrophysicist Arthur Eddington once said, "The law that entropy always increases holds, I think, the supreme position among the laws of nature. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation." Eddington wasn't the only one to see the second law as fundamental. As we've discussed in previous episodes, the second law of thermodynamics may be responsible for the arrow of time and is a key ingredient to solving the black hole information paradox, a solution that may one day unite quantum physics with gravity. But despite these clues to the importance of entropy in the second law, it's not obvious what makes it so fundamental. A system's entropy is what we call an emergent property, and the second law seems to be an emergent law. Emergent properties and laws arise from the statistical behavior of large numbers of particles. For example, a room full of air has a temperature, which is a measure of the average energy of motion of all the individual air molecules. But a single air molecule doesn't have a temperature, at least not in the same way. Instead, that molecule has a velocity and a mass and so on, which define how it bounces off the walls or other particles, giving rise to what we perceive as temperature, and giving rise to the laws of thermodynamics. So, we tend to think of emergent properties and laws as less fundamental than the properties and laws governing individual particles. Entropy is a thermodynamic property, and the second law is, well, the second law of thermodynamics, so is also statistical in nature. Why then are these things considered so fundamental? To answer that, we need to understand what entropy and the second law emerge from. What underlying property of nature do all these different definitions of entropy describe? As is often the case, getting more fundamental means getting quantum. And there is indeed a type of entropy that applies to quantum systems, like our air molecule. It's von Neumann entropy. And understanding it may help us understand not just the second law, but also the arrow of time, and how the large-scale world emerges from the quantum world in the first place. Now, before we dive into that, let's review our more familiar definitions of entropy. To really understand these, we have a full playlist on the mysteries of what I'll call classical entropy and its relationship to information. But let's run through them. Rudolf Clausius came up with the first definition of entropy as essentially the amount of useful work that could be extracted by moving heat energy around. If heat energy is perfectly mixed inside and outside of an engine, then no work can be extracted. While if heat energy is separated, hotter inside, say, the piston chamber, then it will tend to become mixed and we can harness that flow. Ludwig Boltzmann recast entropy in terms of the number of configurations of particles that give the same set of crude thermodynamic properties. For example, there are more configurations of particles in which energy is perfectly mixed than if energy is concentrated in one spot, like in our piston chamber. Systems will tend towards the more common configurations, hence entropy increases. Here we start to see the connection between entropy and information. If all the air is in the corner of the room, for example, then you know more about the positions of the individual particles. They're all in the corner of the room, versus if they're spread through the room. But it took the invention of information theory to really see the connection between information and entropy. It was Claude Shannon who founded the field of information theory and also invented the entropy of information, Shannon entropy. Shannon entropy can be thought of as the amount of hidden information in a system, or more precisely, the amount of information we can hope to gain by making a measurement of the system. If all the particles are bunched up in the corner, then measuring their exact positions gets you some information, but if you measure the positions when they're spread through the room, you increase your information by a lot more. Another way to think about Shannon entropy is in terms of events. The more possible outcomes of an event, the more entropy the event has. For example, a flipped coin is a low Shannon entropy event because it only has two outcomes, while flipping 1,000,000 coins is a high entropy event. Shannon entropy is actually more fundamental than thermodynamic entropy in that it is a generalization of the more familiar entropy. It applies to any system of information and any type of action that reveals that information. When he first came up with this theory though, Shannon didn't fully realize its importance. As the perhaps apocryphal origin story goes, He only started calling his invention entropy after talking to the great Hungarian mathematician and physicist John von Neumann. Supposedly, von Neumann said that he should call it entropy for two reasons. One, it looks exactly like the equation for thermodynamic entropy, and two, nobody knows what entropy is, so nobody would argue with him. But von Neumann probably knew perfectly well that Shannon's entropy was the real deal. One, because von Neumann was a savant-level genius who had out-mathed and out-physicsed many of the greatest minds of the last century. And two, because of part one, von Neumann had already invented his own brand of entropy, von Neumann entropy. It's the entropy of quantum systems. And because everything else is made of quantum systems, it may be the most fundamental definition of entropy. Even Shannon entropy is just a special case of von Neumann entropy. At least, so says von Neumann himself. The concept of von Neumann entropy is at least incredibly powerful. It's at the heart of quantum information theory, enabling us to calculate how much quantum information is contained in a system, and it can also be used to determine how many bits of classical information we can get out of the system when we make a measurement. But perhaps the most interesting, von Neumann entropy tells us the amount of entanglement in a system. In fact, it's driven by entanglement, this mysterious connection between quantum particles that Einstein called spooky action at a distance. As a bit of a spoiler, von Neumann entropy seems to reveal that the evolution of entanglement connections is what drives the second law of thermodynamics.